In this segment, we are going to talk about BGP aggregation and filtering. And when we talk about aggregation, we are really talking about the summarization, the IP summarization. In BGP, this process is called route aggregation for some reason. We are also going to talk about using access lists for filtering of BGP routes. We are going to talk about the AS path access lists, which are really special form of access lists that are used to filter based on the contents of the AS path or the AS sequence list. And finally, we are going to address using route maps for route filtering in BGP. We already know how to set the attributes and how to match on particular attributes using route maps, and we have already talked about filtering using route maps for other protocols, but here we are going to talk about a couple of specifics that we can use with BGP. Configuring IP summarization or aggregation, as I'm going to call it from now on when I talk about summarization in BGP, configuring it in BGP really couldn't be any simpler. All we need to remember is a single command. It's called aggregate address. It's followed by the network, the summary that we are creating, the mask, and some options that are, you guessed it, optional. Now, when we configure the aggregate address, when we configure the summarization in BGP, unlike other protocols, IGPs that is, BGP will by default advertise both the aggregate, the network that we have specified here, and the more specific routes. There is a very interesting reason why BGP does this by default. Very often on the internet, on the worldwide internet, some smaller autonomous systems have their routing configured in such a way that they are not going to accept prefixes that are longer than a certain size. Like, for example, the usual size is /24. However, if we had multiples of, let's say, our /25s or /26s or /24s, we may want to advertise them some this way, some that way, maybe not both in both directions, but that may cause our network to become unreachable from certain parts of the internet if we are advertising only those more specific routes. So what is a usual policy in BGP? What is the usual approach in BGP is that we are going to advertise all our routes to our peers, to our maybe transit providers, to our customers, or to our equal peers. And then we are going to advertise the summary as well. So if one of them or their customers or their peers might be filtering at, say, /24s, they are not going to get all our /25s or /26s, but they might get our larger summary in there. But those who do accept more specifics, they are actually going to follow or send the traffic where we would like to receive it. So this can be used as sort of a very rudimentary traffic engineering technique in BGP. It's a very, very common thing. However, if you don't want to advertise more specifics, obviously BGP does offer a solution for that. So that solution is offered in form of these options that are, as I said, optional. So the solution to advertise only the summary is really just write summary only here where the options say. And you can see here, do not advertise more specific routes. BGP calls this route suppression. Now, it says it is called suppression here because this is how you are going to see them in the BGP table. When you see those routes that have been suppressed by the aggregate, they are not going to be shown as star greater than. They will be shown with a lowercase s and then greater than. This s means that the route has been suppressed by the summary. Another option that is very, very common is to use the AS set attribute. Now, you remember when we talked about the AS path attribute that it has two components. The ordered component, which is the AS sequence, and also the unordered one, which is the AS set. Now, why is this AS set used? Well, if we take a look at the possible scenario, let's say that we have our autonomous system here. Let's say that this is autonomous system 100. And this autonomous system 100 has the peering with the AS200. And this autonomous system here, let's say, has peerings with 3 other autonomous systems. Let's say that this is 65,001, 65,002, and 65,003. And let's say that this that this neighbor here is advertising 10.0.0.0/24, and that this one here is advertising 10.0.1.0/24, and let's say that this one here is advertising 10.0.2.0/24. Now, these three routes can be summarized as a single prefix. They can be advertised as 10.0.0.0/22. Now, that's obviously going to cover one more network here that apparently is not in use, 30/24, but we don't care about that. So this one summary here is going to cover this single, these three networks here. However, this summary is a new route generated by the AS100. So what is going to end up here in the AS sequence component of the AS path is simply going to be 100. That means that this AS200 has lost information that these routes, these component routes, may have originated in 65,001, 65,002, or 65,003, which means that there is a possibility that if there is a connection between these two ASs, somehow this route that may create a loop if it goes back into one of these three ASs is going to create a loop. So if here, when we created this summary, if we used the AS set keyword, what's going to happen is that we are going to have the AS set attribute configured, and there we are going to have information that this was in 65,002, 65,001, and 65,003. Now, I have deliberately listed them in this order here, 2, 1, 3, that there is no order, there is no particular order, and that's exactly what it means that this is an unordered list. So this here is going to be used for loop prevention. So now, when this prefix gets advertised to 65,003 over this backdoor connection that we might see, 65,003 is going to see its own AS in the unordered list, in the AS set list, and it's simply going to reject this update because it has looped. So this is a relatively common thing that is used when configuring the summarization or the aggregation in BGP. Similarly to AS set, we have the option of AS confed set. Now, this is going to be used obviously when we have summarization in the confederation scenario, and this is going to list the ASs, the sub-autonomous systems, the information about sub-autonomous systems when creating the summary. Now, summary only we already talked about. Now, route map here is interesting one. Now, if we have multiple contributors like this, by default, when we create the aggregate, one of these is going to be taken into account to copy the attributes, like the next hop and stuff like that. Now, usually it will be the one that was learned first. So let's say that this one here was learned first. But what if we wanted our aggregate to inherit the attributes of this one here? Well, in that case, what we can do is we can use the route map keyword and match the particular route or the routes that we want to use as attribute seeds. So when the aggregate gets created, actually these attributes will be copied to our aggregate. It's actually a pretty interesting one. Now, suppress map is when it's not used with a summary only. So these two are kind of mutually exclusive because summary only will suppress everything. So the suppress map simply means advertise more specific routes, but not all of them. Advertise only those that match the route map that has been referenced after the suppress map. So we can selectively suppress suppress those more specific routes. Let's now take a look at some of this in action. As you might remember, I do have BGP peering between R1 and R2. And this is an eBGP peering, even though from the aggregation perspective, this doesn't really matter because BGP aggregation is done on the router and then the aggregates are advertised or not advertised to the neighbors. So the fact that this is an eBGP peering doesn't really matter, but it is. So here we have AS 65,001 and here we have 65,234, and you might remember that this is gigabit 1, and we have 192, 168, 12, 0 /24 between them. This is .1 and this is .2. On R1, we have a loop back with the address of 172. Okay, let me fix that. Maybe I should learn to write. 172.16.01/32. What I want to do now is, when I'm advertising this to R2, I would like to aggregate this as, let's say, /24. And I do not want to advertise this more specific. Let's do that. So going to my terminal on R1, first let's confirm that this is in fact what I have. And if I do show IP BGP, here I see that I do have 172.16.01/32 in my BGP table. So this is the one that I would want to aggregate. So going into my configuration, so router BGP is 65,001, and I'm going to say aggregate address 172.16.00, and then I specify the mask 255.255.255.0. And remember, the option that I want to specify is summary only. So now if I do show IP BGP, what I'm going to be seeing here are two routes from 172 range, and here they are. The first one is the one that we just created. This is our summary, and I can see here that the next hop is 0 because this is the locally generated route. But much more interesting output is this one here. As you remember, I did mention that lowercase s will stand for suppressed. So this route here is now being suppressed. It is not going to be advertised to our peers. So if I go to R2 and if I do show IP BGP, what I'm going to be seeing here now is 172.16.00/24, but I'm not seeing that one more specific. Now, I can also see on R2 that I have two routes from 192.168.00 range. So let's summarize these two as /24, and let's advertise this /24 and /32s to our R1. This couldn't be easier. I'm simply going to go to R2 and I'm going to say router BGP 65,234 and address family IPv4, and here I'm going to say aggregate address 192.168.00.255.255.255.0. Now, with this approach, if I do show IP BGP summary, show IP BGP, what I'm going to be seeing here now is that I have two more specifics here, 192.168.02/32 and 4/32, and I can see that they are not actually suppressed. But I also have /24. Now you're not going to see /24 here due to the somewhat classful behavior of iOS. I should really fix this. It is 21st century. Now, second decade of 21st century. Now, if I go to R1, if I do show IP BGP, now here I'm going to see those three routes. I'm going to see /24 that I just created, the summary one, and I'm going to see two more specifics. But let's configure R2 to say suppress the 4. We don't want to send that one. Well, to do that, what we can do is we can go to R2. So now we are getting into the filtering territory. I'm going to create a prefix list. So I'm going to say IP prefix list, let's say R4, and I'm going to say permit 192.168.04/32. So this is the route that I want to suppress. So why am I permitting it? Well, because I'm going to create a suppress map. So here, let's call it suppress map deny 10, and here I'm going to say match IP address prefix list R4. But mind you, at the end of the every route map is an implicit deny everything else. So the fact that I'm denying here doesn't mean much because I will be denying everything else, and I don't want to suppress everything. I just want to suppress a certain prefix. So what I'm going to do now is I'm going to say here route map, and as you will see, this logic that I'm implementing now may come with a surprise. Suppress map permit 20. So I'm going to allow everything else. I did warn you, this is going to come up with a surprise. So now I'm going to go into router BGP 65.234, address family IPv4, and I'm going to, on this aggregate address that I have created, there it is, I'm going to say suppress map. Let's take a look what was the result of this. So remember, this is the command that I typed in, show IP BGP. So which route got suppressed? Aha! I actually had a completely opposite result of what I was hoping to achieve. This route is not suppressed, but this one is. Why is that? Well, here is how this logic works. Let me show you the configuration of the BGP. This is how this logic works. Whatever is permitted by this route map will be suppressed. That means whatever this route map here is denying is not going to be suppressed. So it's a completely inverted logic of the actual filtering. And what have we done? So if I do show run pipe section and we want to see route map, the suppress map here, whatever matches this prefix list is going to be denied. In other words, it is going to be permitted because whatever is going to match is going to be denied. So what we need to do is actually invert this logic. This needs to become permit, and this one here needs to become deny. And the easiest way to fix something like this is to actually bring in your text editor, copy the route map that you have mistakenly configured, and delete it and fix it. So here we are going to have permit, and here we are going to have deny everything. Now keep in mind that this is an optional entry because everything else will be denied by default. But anyways, I like to know what I'm dealing with. So I'm just going to paste this in. And now if I do show IP BGP, well, maybe it is going to take a second or two for this to take effect. Maybe a little bit more than 2 seconds. Let me see if this is correct. Yes, it is. So let's see, show route map. What I'm looking for, suppress map, okay. Well, even the instructors sometimes encounter a problem. And this time the problem was entirely right here. Let me show you. So if I do on my R2, if I do show IP BGP, what I'm going to be seeing here, and this is something that I have not actually been looking at, it was staring me in the eyes, is that this prefix 192.168.0.4 actually is in a rib failure state. It means that there is a route from a better routing source inserted in a routing table. Now, what I was expecting to see here is that it's being suppressed, but R will actually override S. All I had to do was actually do show IP BGP 192.168.0.4, and here is my answer. It says here advertisements are suppressed by the aggregate, and I can see here not advertised by any peer. And if I go to R1, I'm actually going to see that. There it is. We have 192.168.0.2/32 is being advertised. That's the one we wanted to have. And here we have 192.168.0.0, and remember this is /24 here. So we have our aggregate, and we can see that the other route was actually suppressed. Now let's talk a little bit about route filtering, and more specifically, route filtering using access lists. Access lists for route filtering in BGP can be used in multiple locations. They can be used globally, and by globally I mean in the whole process, or the address family if you are using the address families. If you are using that, you can reference the access list from the distribute list, you specify the access list, and whether you want to filter the routes in or out. And this will apply to all neighbors except for those neighbors that have more specific filtering configured. And by more specific filtering I mean unless they had per neighbor distribute list configure. If you configure the distribute list on the neighbor, the syntax is neighbor, you specify the neighbor's address, distribute list, whatever the access list is, either in or out. And in that case, this access list will be used for filtering the routes either received, the inbound routes, or the routes being advertised, outbound filtering. And we can also use access lists inside the route map. So there are, generally speaking, 3 ways we can use access lists for filtering BGP routes. But we know that there are standard access lists, and from the previous examination of other routing protocols, we know that the problem using standard access lists is that they cannot match the prefix. They cannot match the prefix length. So if we had network/mask with the standard access list, we cannot match the mask. The only thing that we can match is the network itself. Now, if you wanted to use access lists for filtering and you wanted to match the net mask, you need to use the extended access lists. Now, using extended access lists for this purpose changes the way extended access lists actually behave, and this is a special BGP behavior. It's not so special for BGP because it exists in some other conditions, like for example, route leaking from level 2 to level 1 for ISIS routes, and also in route redistribution route maps, this behavior of extended access lists can be exploited, can be used. Now, what I'm talking about is using the source IP address in the extended access list to match the network, and also using the destination in the extended access list, destination IP address, to actually match the net mask. What I'm talking about is writing an access list that looks something like this. So I'm going to say access list 100 permit IP, and then say, for example, host 192.168.0.0, host 255.255.255.0. Now, when you first see this, it looks very unusual and very confusing because, I mean, what does this even do? What does this even mean? Now, I made a mistake here. It's in 2 lines here, so let's try to extend this a little bit. There we go. This is what I wanted to have. So, when you first see this, this makes no sense. But once you examine what I said before, now this part here, this is defining the source, and this here defines the destination. Now we know that the source will be used to match the network part, and we know that the destination here will be used to match the mask. So what we are saying here is permit those routes that match this network exactly and this net mask exactly, because this host 192.168.0.0 is really equivalent of writing this. Now this here simply means that this octet needs to match exactly, this octet needs to match exactly, this one needs to match exactly, and this one needs to match exactly. Same thing here when we write 255.255.255.0.0.0.0. What we are really saying is that this octet here needs to match exactly, this one here needs to match exactly, this one here needs to match exactly, and this one here needs to match exactly. So using extended access lists for BGP filtering is a little bit counterintuitive at first, but once you figure out this logic here, it becomes very, very easy. Not to mention extremely powerful, because you don't have to use the host here. We could do something along these lines. We could say here in this part, we could say 192.168.0.0, and then here host. Actually, I'm just repeating what I said, so let's change something. 0.0.255.0, and then host, and then basically repeat this here, so 255.255.255.0. So what do you think this syntax here does? Oh, oops, made a mistake there. So what do you think this does? Well, basically what it does, it says this octet here needs to match exactly, this here needs to match exactly, this one here, well, we basically don't care what's in this octet, and this one here needs to be match exactly. Now, that means that we have 192.168 whatever 0 with the mask of /24. So basically what we are saying is match all the routes from this range, basically from 192.168.0.0/16 range, as long as the mask is exactly /24. There you go. It's very, very interesting. Now we can do the same thing with prefix lists, but with access lists there are a couple more things that we could do. We could, for example, configure this to match only even or only odd subnets here. I'm not going to be showing you that example, but with access lists, because of the power of the wildcard masks, this is something that we can do. But the important thing to remember, truly important, is that when you are using standard access lists for BGP filtering or for any route filtering, you cannot match the mask. You cannot match the prefix length. If you wanted to do that when you are performing filtering with BGP, you have to use extended access lists. Now we are going to talk about filtering in BGP using AS path access lists. I should warn you that this is the topic that usually gives students the most difficulty when they are studying for BGP filtering. Now, the reason for that is that BGP filtering using AS path access lists requires you to approach the AS path not as a series of numbers, but as a series of characters, or as a string, as it is called in our lovely computer science. Now, to understand how BGP can filter based on the AS path, we have to first make some things clear. The beginning of the string is the end of the path, and at the end of the string is the beginning of the path. What I mean by that is when we have a series of autonomous systems where the route has been learned, we know that the first autonomous system, the origin autonomous system, is going to be at the end of the string. Then we are going to have all the others that this route may have gone through, and finally we are going to have the AS that we learned the route from, or our peer AS. Now, all these numbers here are really just series of characters. This is 500 followed by space, 400 followed by space, 300 followed by space, 200 followed by space, 100 followed by space. But this is not all. At the beginning of the string here, there is a hidden beginning of the string character, and here at the end, there is the end of the string character. This is represented by the caret sign, and this one is represented by the dollar sign, in a concept in the technology called the regular expressions. Regular expressions, or regex or regex, depending on your pronunciation, are pattern matching mechanisms that are utilized by many programming languages and to some extent by iOS. And in iOS, the regular expressions can be used for all sorts of things, and today we are going to talk about using them for BGP filtering. But as I said, before we can start talking about the regular expressions and before I can start talking about the actual filtering, we have to understand these concepts, that this is our AS path as a single string, as a series of characters that has the special character, the beginning of the string, at the beginning of the line, and the end of the string at the end of the line. But we know that the AS path is actually built in this direction. So we really have to read this AS path in the opposite direction, and then we would normally read it. Now, we know that this AS500 here is called the peer AS, and that this one here is called the origin AS. We also know, and we talked about this before, that these here are really transit autonomous systems, and sometimes this may include 500 and also 100. So they're all really, in some sense, transit. Well, maybe not 100, but 500 definitely a transit AS. Now, our own AS, the AS in which we are observing this path, is actually not in the list. It's here. It will be added to the path when we advertise this prefix outside our own autonomous system. So when we are talking about the filtering based on the AS path, as you might have guessed it, we are actually talking about filtering about the contents in the AS sequence. So going back here, we mastered that the beginning of the string is the end of the path and the end of the string is the beginning of the path. The next thing is the autonomous system numbers are really not numbers. Don't think of them as numbers. If you think of them as numbers, you are going to have trouble implementing filtering. What do I mean by don't treat them as numbers? Well, if you take a look at this here, and you are now saying, yes, this is 400. No, this is character 4 followed by 0 followed by 0. This is how I want you to think of this. Not about the number 400, because using regular expressions, you cannot match 400, but you can match 4 immediately followed by 0, immediately followed by 0. How do you write a regular expression for that? Well, it's very easy, in fact. Surprisingly easy. There it is, 400. But it's not number 400 that we are matching. It's a series of characters, 4 immediately followed by 0, immediately followed by 0, surrounded by AS number separators, or the autonomous system separators. So what are the ASN separators that we can use in the AS path? Well, there are a couple of them. Start of the line, it's a separator. End of the line, it's a separator, or the white space, it's also a separator. Now, all of these can be matched individually. We can match start of line with the caret sign. We can match end of the line with the dollar sign, and we can match white space by simply typing a white space. But that is going to be challenging in iOS, so what we can use is underscore to match for space. There is a side effect of underscore that it is actually going to match the end of the line and also the caret and also the white space. But anyways, we can use it to match any separator. So any separator will be matched by using the underscore. But also we can have other separators, like parentheses in a case of subautonomous system numbers if you are using the confederations, or curly brackets. If you see curly brackets in your AS path, what we are dealing with are the contents of the AS set. So AS set can also be matched using our regular expressions, but the primary filtering that you are going to encounter is going to be based on the AS sequence. So going back here, let's talk a little bit about regular expressions for AS path filtering. First of all, let's take a look at some of the basic matching patterns. If you use digits from 0 to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, this is going to match individual digits. So if, for example, we had the regular expression that simply said 5, so let's say that this is our regular expression. This will match AS path that looks like this. It will match this. It will match anything as long as 5 is encountered in it. So here we have 5. Yes, it's followed by several 5s, but it's still the digit 5 has been encountered in here. So not very useful, but this is how it works. Now, if we use the dot, a single dot, this can match any character. It will match any digit, it will match any separator, it will match any of the special characters that we might encounter. We already mentioned that the caret and the dollar sign match the start of the line, remember, end of the path, and also the end dollar will match end of line, which is the start of the path. And underscore will match any of the separators, white spaces or the beginning of the line or the end of the line. So these are the basic matching patterns that can be used when we are matching for particular AS numbers. So how would we match, for example, the AS 100? Well, think about it. AS 100 is 1 immediately followed by 0, immediately followed by 0. 1 is preceded by a separator, and last 0 is followed by a separator. So underscore 100 underscore will match AS 100 anywhere in the AS path. Now, how would we match AS 100 if it was originating AS? Well, easy. We know that it needs to end with 100, so it's 100 surrounded by any separator, we don't care about it at the beginning, and at the end, immediately followed by the end of the line. How would we match, for example, the AS number that consists, AS number 200, that we learned the route from our peer AS? So remember, this is the peer AS here. How would we match, let's say this is 500, how would we match this AS number? Well, simply, we know that the string needs to begin with 500 followed by any separator. So this here will match the peer AS 500. So this one will match any transit AS. This one here will match origin AS, and this one here will match peer AS. But how would we use the regular expression to match the routes that originated in our own AS? Think about it. What is going to be the AS path of those routes? It's going to be beginning of the string, immediately followed by the end of the string, an empty string. So this would match our own prefixes. So these are just some examples of the regular expressions that you might want to use. There are some advanced concepts in the regular expressions. I'm just going to quickly mention them here. The brackets, the square brackets, they match listed characters or ranges. Now, what does that mean? So, for example, if we used 1, 2, 3 in brackets, this is not going to match 1 immediately followed by 2 immediately followed by 3. This is going to match 1 or 2 or 3. So this is basically a list of characters that can be matched in that particular position. But we can also use it to match the ranges of characters. So for example, 3-7, this is going to match 3 or 4 or 5 or 6 or 7. So this dash here is not a literal character. It is interpreted as a special character that means, okay, this is the range that we want to match. But what example if we wanted to match 750? Well, we already know that just typing it like this is enough. But typing it like this is not very useful if we wanted to use something called the modifiers, which I'm going to mention a little bit later. So we can actually provide this as a group of characters. So now this 7 immediately followed by 5 immediately followed by 0 is treated as a group of characters. Now, even better if you wanted to match 750 would be to actually put it like this. Now, this in parentheses from a regular expression perspective is considered to be a single matching pattern. It's a single entity. Now, this brings me to modifiers. Now, these are star or a plus, and they are used after the pattern that you are trying to match. So, for example, if we had, let's say, let me use another example. If we had 5 star, this means that this 5 may or may not appear, and if it appears, it's okay if it repeats 1 or more times. So this will match, basically, this. It will match 5, it will match 5, 5, 5, it will match 5, 5, 5, 5. So all of these will be matched by this matching pattern here. Now, when you look at it like this, not very useful, but 750 star, this means that number 750 may or may not appear in our AS path, and if it appears, it may repeat multiple times. So this will match 750, 750, or it will match simply 750, or it will match AS path that doesn't show it, but it will match 750 repeated any number of times. Again, can be useful, but it's not necessarily always useful. A much more useful modifier, if you ask me, is a plus sign. Now, what does the plus sign do? Well, what plus sign does is, let's say that we had 750 plus. What plus says here is that the immediately preceding pattern, and mind you, because we are using parentheses, this means that the group of characters specified here needs to repeat, needs to show up. This group of character needs to be matched at least once, so it must appear, and then it may or may not repeat multiple times. So this will match 750, or 750 followed by 750, or 750 followed by 750, followed by 837, for example. This is okay, because we have one match here. There it is. We have a match. Then, yeah, it's okay to repeat itself, and then we have 837 here. Now, if we wanted to match this particular string here, what we could do is we could write a regular expression that looks like this. But what if 750 appears 3 times? Then this fails. So we could write the same thing somehow like this. There we go. Now this matching pattern here will match this. Why? Because we have 750, it has to appear at least once, check. And then it may or may not repeat itself, okay? It does repeat itself, 837. This will also match 750, 837. Why? Because here 750 has to appear at least once, check. And then it may or may not repeat, doesn't repeat, that's okay. Immediately followed by 837, check. But this pattern here will not match this. Why? Because we don't have a match on 837. Or it won't match this one here. Why? Because we don't have a match on 837. If the AS path was, for example, 555, it won't match. Why? Because none of this appears in this AS path here. But mind you, if we used star here, in that case, for example, just 837 in the path would be a match. So we are saying 750 is optional as long as there is 837 there, but we are going to accept it even if it's immediately preceded by any number of occurrences of 750. Regular expressions are incredibly powerful tool, so it does help to learn them a little bit, to spend some time practicing them, and you can do that if you have access to any of the routers that have access to the full BGP routing table. It's a very, very good place to start. Now, if you don't have access to any BGP speakers yourself, a good place to actually go and practice is traceroute.org. So let me just write that down for you here. So it's traceroute. And if you go to this website, you can find something called route servers, which are publicly operated routers that run BGP that allow you to run certain BGP show commands. And there is a BGP command that you can use to practice the regular expressions, is show IPBGP regex and then followed by the regular expression. So you can practice to figure out the routes that may have originated in certain AS, or that they have been learned from some AS, or that have been in transit in a particular AS. So now finally we can talk about the AS path access lists. First, AS path access lists are defined as AS path access list, and then we specify the number of the access list. And then we can either specify whether we want to permit or deny whatever regular expression that we used. And we are going to use the regular expressions that we just learned. And then we can use these access lists either directly on the neighbor using filter list, where we specify this access path, the AS path access list, either in the inbound or the outbound direction, or we can reference them from the route map. Now, I'm going to pause here and talk a little bit about the syntax in the route map. So if you are using route map, so let's say that we had route map, and we say match AS path 10. It's very, very confusing that this number 10 here actually references the AS path access list, not the actual AS number. So be on a lookout, because when you are taking, for example, some Cisco exams, they could define an access list, the AS path access list 10, that actually matches, for example, 9. And they say, okay, configure your route map to match the access list, to match the autonomous system 10. And then you think to yourself, okay, well, it's right there, there is 10. But no, it is actually matching the AS number 9. So be on a lookout for that. It's very, very important to remember that in the route map syntax, the number that we are using here is actually referencing the predefined the AS path access list and not the AS path directly. So let's take a look at some of the examples. I already mentioned a couple of these, but here they are written in the actual syntax used for AS path filtering. So in this first example, in the AS path access list 1, what we have here is AS path access list 1 permit underscore 100, or I should say underscore 100 $, which basically will match any prefixes that originated in AS 100. Well, why? Because we are reading this backwards. So we have the end of line, the beginning of our path, immediately preceded by 100, immediately preceded by any separator. Now, mind you, separator can be white space or can be the beginning of the line. That doesn't matter. Our requirement was simply to match the routes originated in AS 100. Similarly to this, our AS path, access list number 2, that looks like caret 200 followed by the underscore, will match any routes that we actually learned from AS200. Again, reading this backwards, this means that we don't care what's after this or what was really before this in the AS path, but the AS path ends with 200. Why does it end? Because this is the beginning of the string, and the beginning of the string is the end of the path. Again, in AS path, access list 3, we have underscore 300 underscore. This will match routes that were in transit in AS300. But keep in mind that written like this will actually match these three. So if you wanted to match only those routes that were in transit in 300, but they were not, for example, originated. Actually, it's going to match one more. I forgot about that one. So it's going to match this one as well. So if you wanted to match only those routes that were in transit, but they were not here, what we would actually have to do is we would have to write an AS access path that consists of multiple entries. We would have to have a first deny and then permit. I'll give you that example a little bit later on. So the next example here is AS path access list number 4, and this one will match routes from our own AS, the empty string. Similarly to this, a very special case is this access list number 5, which looks like this, dot star. Now remember, dot matches any character that may or may not appear or repeat itself. So what is dot star? It matches all routes. It matches everything. So in regular expressions, this means everything. The next one, for example, is this two-line entry. So here we want to deny routes that were originated in AS400. This is what we do, and permit everything else. Now, if we take a look at the example of 300, if we wanted to match the routes that were in transit in 300, but they did not originate in AS300, what we could do here is we could say 300 here, and here we could say underscore 300 underscore. So we would deny those that actually originated in 300, so they would be denied, but all the others that were not originated in 300 but were in 300 in transit would be permitted. So these were some of the examples of using the AS paths for filtering, or using the regular expressions for filtering based on the AS path in BGP.